Uh, I would like to thank to organizers, Reynold, Frank, and Lot, organizing this wonderful meeting and also program. 3 years ago, I started this project 4 years ago. Then at that time, I presented some preliminary result. Then I had a lot of comment from participants, and then we could develop this project more. So thank you very much. And little bit. So today I want to talk about discrete integrable system with self-adaptive moving mesh. And this is a joint work with Baofeng Feng and Yasuhiro Ota. And also geometric approach is joint work with Kajiwara-san and Inoguchi-san. Okay, so not good color, so a little bit difficult, but yeah, I will talk about self-adaptive moving mesh difference equations, and yeah, but then today I will show a couple of examples, short parts, coupled short parts, Hunter-Saxton, Kamas-Holm. But we have more examples, but probably we probably explain some example here. But also I will talk about discretization of WKI elastic beam equation and curve shortening equation by using geometric approach. First, I use Hirota's discretization method based on tau function and bilinear equation. But then this one is based on the motion of discrete curve. And especially here, curve shortening equation. This is a non-integrable system, one of famous equations in pattern formation. But based on geometric approach, we can get nice discretization. And this discrete curve shortening equation has also self-adaptive moving mesh property. Okay, so now let me explain the difficulty about numerical computation for large deformation phenomena. For example, suppose you have some, wave, but here around the peak, some singularity or shock. And for example, if you have finite difference scheme, then if your peak is between mesh grid, and here you have here peak, but then numerical scheme, just compute point on mesh grid. So this means here this part you will not get to data, okay, between mesh grid. So this means if you compute this kind of phenomena, large deformation phenomena, using finite difference scheme, then if something happens here, then if you compute this using this numerical scheme, then you will lose a lot of information. Then finally, you will get bad result. This is a problem. So that's why around 1980, people in computational physics and numerical analysis, they introduced adaptive mesh refinement method. This means they, around some large deformation behavior, you can make more grid. Like you can refine mesh, and then you can, some part, you can make more and more grid. Then you can compute more, difficult computation you can do. But there are two famous refinement methods, and one is static mesh refinement. If the location of singularity, if you can expect this region, you can use just static mesh refinement. This means here example, around the boundary, you can make many grid, and around here nothing happens, so you can make a rough grid. This is static mesh refinement method. Another one is dynamic mesh refinement. If the location of singularity move, then you must now change the location of many grid. This means for example, if you have wave phenomena, like here, you have wave phenomena. Now this is moving, so this means here, around here, here another example. Here you have now, okay, peak, and here you can make many points around peak. Then you can now compute many points between this mesh. So then finally you can capture this phenomena. But then now if this waveform move, then you must change. You must also move this mesh grid. So this is very difficult because, okay, if this is dynamical phenomena, then this location is now moved. Then you must also move mesh. But then this is very difficult. So usually in engineering and computational physics, they're making a good algorithm for adaptive mesh refinement is very difficult. They are trying to make a good algorithm right now. So now we thought now finding good algorithm of dynamic mesh refinement is very important for numerical computation. And then we thought, are there integrable dynamic gridding schemes? This means discrete integrable system with automatic adaptive mesh refinement. So up to now, there are no such kind of discrete integral system. Like you have some integrable system, but then, if you have some peak, but then around the peak, we have many grid point. And then this grid point now move. We want to make such kind of discrete integrable system. And to do this, okay, to make this kind of discrete integrable system, now we considered Kamath-Holm equation, short pulse equation, and some WKR elastic beam or Hardy-Dim equation. These equations have singularity in solution. So probably very good. Probably these gives some good example for making discrete integral system with self-adaptive moving property. So up to now, before we do these integrable systems, there are no integrable discrete scheme. So that's why we tried to make numerical difference scheme for these equations. So now, okay, objective is now develop method to discretize these PDEs, keeping the integrability, and then we want to find the develop effective numerical method for nonlinear PDEs, which describe large deformation phenomena. Okay, and if possible, we want to extend this method to non-integrable system. So now first we want to use Hirota's discretization method. So now probably everybody knows what is Hirota's discretization method. Transform a nonlinear differential equation to bilinear equation. This is the first step. And then discretize bilinear equations. And then transform discrete bilinear equations into a nonlinear form. And using this procedure, Hirota sensei made many discrete equations. So this is effective. So now we want to try to discretize this short pulse equation. This is relatively new. 2004, Schaefer and Wayne, they found this equation from Maxwell equation. This equation describes some phenomena in optical fiber. And this equation has an interesting solution, like Breezer type solution. This is large deformation. Also there is loop type Soliton solution. Okay, now we want to discretize this. And then now we can now consider the transformation about U. Now here tau function f and f star. And now in this equation, key point is there is Hodograph transformation. This means the solution is parametric form. Okay, so using now this Hodograph transformation, now you can write down the solution of short pulse equation. And this equation is related to Sine-Gordon equation. And then, now, important thing, this short pulse equation, now, you can apply Hodograph transformation, this, and then this short pulse equation will be this form. And this form, this is coupled form, and first equation is conservation law. Law is conserved density, and second equation is some integrable equation related to Sine-Gordon equation. And now, consider bilinear equation of short pulse equation. And this is actually bilinear equations of Sine-Gordon equation. And this is a determinant solution. So now discretize this bilinear equation. And of course, this is already known, Hirota sensei did. And this is actually semi-discrete bilinear equations for short pulse equation. And these bilinear equations have this determinant solution. And then now, okay, in continuous case, okay, we had Hodograph transformation. This. Now, because here, this is integral about x1. This is a space variable. So now we want to discretize space variable. So now, of course, you must change this one, integral, into the summation. Okay. After using this, now this, okay, then we can now recover the nonlinear form from the discrete bilinear equation, and we will get these coupled equations with discrete Hodograph equation. And this is actually, you can see this one. First one is actually discrete conservation law. This law K is conserved density. And second equation is discretization of here. So this is a continuous case. Okay, here first one is conservation law, second one is this integrable system, but then discretize. After discretization, okay, you will get this. So this is integrable, actually integrable analog of short, integrable discrete analog of short pulse equation. And now you can see this is a coupled form. But this log k is, what is log k? Log k is xk plus 1 minus xk over a. What is xk? xk is mesh point. This is grid point. This means now log k is actually mesh interval. So this means the first equation is the evolution equation of mesh interval. But this mesh interval is actually conserved density. Okay? So now conserved density become mesh interval. Then first, now you can get the mesh interval. Then after using mesh interval, then you can now solve this equation. You can get the value. After you get the value, you can go back to this. You can generate the mesh. And after you get the mesh, then you can also compute the value. Then you can solve this. Okay? So this is self-adaptive moving mesh. And now first equation, okay, in continuous case, okay, we had conservation law. But then after discretization, we got a discrete conservation law. And this provides the evolution equation of mesh point. Okay. And now you can just check this equation, first equation of system. But this is actually log k is because log k is this. That's why this means first equation become like this. So now if you check this, you can understand this phenomena. Actually, okay, log k is conserved density, and this is mesh interval. Oh, sorry. This means this means from this is conservation law. So this conservation law. This means if log k mesh interval increase, if f of uk plus 1 is greater than f of uk. So this means now, okay, if right hand side is positive, this means now log k, okay, derivative of log k, now it becomes positive. This means log k increase, okay. Then if f of uk plus 1 is less than f of uk, then log k, because derivative of log k become negative, this means log k decrease. This means, this conservation law provide, okay, sometimes mesh, many mesh, sometimes, not many mesh, So this conservation law actually create the moving mesh. Okay, you can understand from this conservation law. And also now using also you can also discretize time part, and if you discretize time, you can also get full discrete analog of short pulse equation. But this is very interesting because actually here x and u, this is a coupled equation about xu, but then here there is some identity. Always, okay, these relations must be satisfied. This means this gives a conservation law. Yeah. Yeah, fully discrete. Integrable. Integrable.
Has symmetries and everything.
Oh, we didn't check symmetry.
What does it have?
N Storyton solution. This means Casorati determinant solution. And also we can also consider this coupled short pulse equation. This is generalization of short pulse equation, and you have many components. But this one also you can rewrite in this form. Okay. So now first equation is again conservation law, and second equation is actually same equation to short pulse equation. But you have many fields. Okay? And here this is Hodograph transformation for coupled short pulse equation. This is the same as short pulse equation. This one we can also discretize this. But this one is these are bilinear equations for coupled short pulse equation, and the solutions are written in Pfaffian form. And then we can discretize these equations. Now these are semi-discrete equations for coupled short pulse equation, and these bilinear equations have Pfaffian solution. And using this, we can now create the integrable self-adaptive moving mesh scheme for coupled short pulse equation. And this is actually very similar to the single component short pulse equation. Actually, second equation is the same, just you have many fields. And first one, but you have coupled, okay, term, okay. And here, Hodograph transformation is same as previous one. So you can do like that. And another example, Hunter-Saxton equation. This is actually short wave limit of Kamasatorm equation. Okay. So then, for example, Kamasatorm equation have more extra term, but this is much simpler than Kamasatorm equation. And here, using this transformation and Hodograph transformation, you can write down Hunter-Saxton equation into bilinear equations. And here also we can write down this equation in this form. Again, here first one is conservation law, and the second one is actually hyperbolic sine Gordon equation. With Hodograph transformation, you can rewrite Hunter-Saxton equation into this form. Then now we want to discretize this, but then here this is a bilinear equation of Hunter-Saxton equation, but now discretize this. We will get the bilinear equations of this. Then we will get this equation. This is the self-adaptive moving mesh scheme for Hunter-Saxton equations. Okay. And again, this is again first equation is discrete conservation law, and second equation is a semi-discrete analog of hyperbolic sine Gordon equation. And first equation gives the evolution equation of moving mesh, and also second equation. After you determine the mesh grid, you can solve the second equation. You get W. Okay, then you can use this scheme for numerical computation. Here we didn't discretize time because time evolution you can use some symplectic Euler method or Runge-Kutta method, and you can get a good solution using those known numerical method. But also you can also discretize time also. Then here problem is before I can show here in this case Hunter-Saxton equation here Hodograph transformation has integral about x inverse, but this x inverse is time variable. So when you discretize space, you don't need to discretize this x inverse. So that's why here, actually, after you discretize space, still, here you can include the integral. But now, when you discretize time, you must consider discretization of this photograph transformation. But then, in this case, actually, for discrete case, you can actually, this integral you can rewrite in the summation of actually mesh interval. Okay? So this is fully discretization. And I will skip Kamasorum. This Kamasorum is almost similar. And then next example is WKI elastic beam equation. This is actually very old equation. But now, when we want to discretize this. This is relatively complicated. So using bilinear method, we couldn't discretize this. So now we considered another method based on geometry. Okay? Kajiwara-san, in Wednesday, Kajiwara-san talked about the motion of discrete curves. And he explained MKDV describes the motion of curves. Okay? So now, but in this setting, okay, here MKDV equation, what is variable s? This variable s is arc length parameter. So coordinate is arc length. So now, if we change the coordinate from arc length s to x, x is Euler coordinate. Okay, now consider x coordinate, then y coordinate. Here, this is Eulerian coordinate. If we use Eulerian coordinate, now we rewrite this equation using Eulerian coordinate. What happens? Now, actually, transformation from the arc length parameter to Eulerian coordinate is actually this gives this photograph transformation. And using this photograph transformation, you will get WK elastic beam equation. And this means WK elastic beam equation and MKDV equation describe the same motion of same motion of continuous curve. Okay. So this means actually these two equations are same. Okay, from the point of view of geometry. And then actually now we want to discretize this following Doriwa-Santini or Kajiwara-san's talk. Then now we consider the discrete curves here. And now everything we follow Kajiwara-san's talk. And then here we get the discrete Fourier equation and the time evolution. And then compatibility condition, we have the evolution equation of motion of discrete plane curve. And as Kajiwara-san explained, if we give the f, here f and g can be any function, but f and g, if we give these function and values, we obtain semi-discrete MKDV equation. Okay? Now, this is actually semi-discrete MKDV equation means this describes the motion of discrete curve, but the coordinate is arc length. So now change to Eulerian coordinate. Now consider this picture, then we have now here mesh point. Now change to this point. Then discrete setting, the transformation, photograph transformation is this. Using this photograph transformation, we can obtain semi-discrete WK elastic beam equation. This is again first equation, the evolution equation of mesh, and second equation gives the value, okay, of V. So this is again self-adaptive moving mesh scheme. And using the same formulation, okay, here you have the evolution equation of the motion of continuous plane curve. Okay. Now, if we set f is kappa, then you will get g is this. This means now this evolution equation will be the differential integral equation. Now, in this case, if you change the coordinate to Eulerian coordinate, now you will get curve shortening equation. This is famous equation in pattern formation. Okay. So now, again, this equation, okay, here continuous. This equation describes the motion of continuous curve. now we use now discrete curve. Okay, just we use different f and g. Then actually, if we compute a little bit computation you need, but if you compute this, then you will get this semi-discrete curve shortening equation. Okay, this is again, okay, first equation, the evolution equation of mesh, and then second equation you can solve this, then you get the value of v, and you can do some numerical simulation of curve shortening equation, which describes some pattern formation in viscous fingering or something so on. Okay, so this is a non-integrable system. So now I explained some integrable self-adaptive moving mesh scheme and also non-integrable self-adaptive moving mesh scheme using Hirota's discretization method and also geometry approach. And so as you saw many examples, actually, although, many examples, different cases, but still, the equations obtained are very similar form. So first equation is actually gives the evolution of moving mesh, but that is related to conservation law. And second equation, after you get the mesh, then you get now using the second equation, you can compute the value of discrete equation. And then you can use G's scheme for numerical computation. Okay. So thank you very much. Yeah.
Questions, please? No kills. Yeah. No warrior.
Oh, I forgot. Yeah. That's most important. This is most important. Sorry. Thank you very much. Yeah. Oh, yeah. So here, many mesh. So around the peak, the main lot of mesh. That's why we can simulate these phenomena.
These simulations are discrete or discrete continuous? You're integrating continuous time to get these animations?
Oh, these numerics we are using symplectic Euler method for time evolution. So we are using semi-discrete equations.
Can you show me the conservation law you use to derive holograph transformation?
This one?
Oh, it's later. Yeah, this. So the red one in the middle of this slide, it is a trivial conservation law.
You can integrate.
Yeah, because both sides are different. I mean.
Yeah, actually, you can make a single.
It's not conservation law. It is trivial, right?
It's almost trivial, but using trivial conservation law, we can. Yeah, this is.
With a reciprocal transformation, you can get non-trivial sometimes from a trivial transformation.
A comment, actually maybe two comments. So in the world of PDE theory, this notion of using a distribution function, rho, which is this density function, people often select or have to have a selection mechanism for how you update the grid. So there they have an equidistribution principle. So what's interesting to compare is that you've got an integrability condition as a selection mechanism. So it'd be interesting to look at the literature and see where equidistribution and this integrability overlap.
Yes, that's right now there are many algorithms, but still people are investigating good algorithm.
Yeah, so the second,
So-
second comment
yeah.
relates to the motion by mean curvature. So there's quite a large community that works on something called crystalline mean curvature
yes.
flow. So have you compared your algorithm to the crystalline mean curvature?
Yeah, that's actually I want to do actually, but this result, final result, curve shortening equation recently we obtained. So, but
That'd be fun to
yeah,
look at.
yeah, that's we want to do actually. Next step. Yeah.
Kenichi, can you make some comments about the Gaspers Purchasing? What have you
Yeah.
done with the Gaspers Purchasing so far?
Yeah, but yeah, that's I was thinking, but this time I didn't present. But yeah, you know, as you know already, Kamasolum we did. Then, but difficulty of discretization of the Gaspers equation is a little bit difficult because this is related to Steka equation. Steka equation. Then you know, discretizing Steka equation. We recently had some result, but there are some discrete Steka equations. So still, we are trying to compare with other results. Wolfgang is that.
Last question here.
Yeah. So since you just mentioned the Titeka equation,
Yeah.
so there are Monge pair type versions of, say, the Sine-Gordon equation and the Titeka equation.
Yeah.
So if you, and the connection between these Monge pair type equations and these equations is just the sort of classical characteristic equations. So you have these classical characteristic coordinates. So if you're trying to discretize these Monge pair type equations, for instance, for the Sine-Gordon and Titeka equation, then you can exactly use your approach, and you, by doing this, you actually discretize the classical characteristic equation.
Yeah.
So we did this for the Titeka equation and the Sine-Gordon equation. So it's very good because one can see it actually works for all types of equations.
Yeah. I agree.
Okay, let us thank the speaker again.